Hey everybody, welcome back. This is Ripley again. We're in chapter 2 now. We're starting to talk about data a little more intensely. Start digging into it for real. Remember that part of the definition of statistics was the gathering, the organization, and the presentation of data, and we draw conclusions based on that. So we're going to take a kind of a visual approach to looking at data. And there's a little acronym. What the heck? I guess it is sort of an acronym. It's more of a mnemonic to remember the characteristics of data, especially when you're looking at a graph. I think most of us are familiar with histograms, bar graphs, things of that nature. But what we're going to start looking at those things quite a bit differently, especially once we have the information. So the mnemonic that we're going to use is CVDOT or SVDOT. I don't know what that means, but let me show you what I'm talking about. So C stands for center. In other words, where's the center of a distribution? So if I'm looking at some sort of a bar graph or something like that, and it looks like that, all right, for example, where is the center of this data? What does this really mean? I mean, what am I looking at? I got to look at the axes and see what they say. You know, what is the vertical axis measuring? What's going on here in the horizontal axis? And where would the center be? The way I like to think about the center is, if I were to balance this thing along the x-axis here, where would that balance point be? Would it be all the way over here? Probably not. The thing would tip that way, right? Would it be over here? Likewise, it's going to tip that way. So it's going to be, I don't know, somewhere in here, right? So that's where the center lives. Most of us think of the center as the average, or you may have even heard of mean, but that's not necessarily going to be the case, all right? And there's something called variation. Variation is how widely spread apart is the data, right? So if I'm looking at this guy versus, let's say that the scale is preserved on this, versus, say, this guy. Notice that this data, again, as scale is preserved, is far more spread out, which means the variation of the data is a lot wider. Again, if we were to look at center, I don't know, if you put a gun to my head, I'd probably guess somewhere around there, okay? D is for distribution. Distribution. All right. Distribution is what's the shape of the distribution? What's it look like? And this guy's got a real clean shape. It's kind of got this weird tail going on over here. This has sort of a bicameral. It almost looks like a camel's hump, doesn't it? So you pay attention to those kinds of things. What does the distribution look like? O is for outliers. Outlier data is data that is outside of the pattern. So on this distribution, if I was looking at the data, these values out here would be considered, could potentially, be considered outliers, because most of the data is grouped around in here. But these guys out here, they're way away from the center. The center is a nice landmark that we can use for sort of justifying outliers. Notice in this, there's no data, you know, way out here. So like if this guy all of a sudden had a little guy over here, you'd be like, whoa, what's this guy doing? Or something sitting over here by itself. Those might be considered outliers because of their distance from the mean or the median, which we'll get into down the road. And then last but not least, depending on the type of distribution that you're looking at, how the data is being presented, we can talk about time. All right, T has to do with time. So in the case of this, what we're looking at right here, time doesn't appear to be a factor, but we've all seen like a stock market chart. So you know, if you've got, it goes up, and then after a day it goes down, and then in 2008 it goes way down, and then it comes up. And now in this case, this is called the time series graph, which we'll talk about it. Let's say that the vertical axis is how much my stock portfolio is worth, and this is time, and this would be about right here, about $17. Okay, so that's this CV dot is a good mnemonic to remember, sort of what to have in the back of your head when you're looking at a distribution, when you're looking at how data sort of displays itself. Okay. All right, now we're going to talk a little bit about something called a frequency distribution. And a frequency distribution is simply a way to organize data. So we have that mnemonic device back here that I showed you. this CVDOT. But the problem is for this to be really effective, for you to start getting an intuitive feel for how this works, you have to have a distribution. You have to have some sort of graph to look at to start sort of playing with the data. When the data sits like this, let's say that I walk into a freshman PE class and I weigh all of the boys, all right? I think there's 28 values here. We'll figure that out in just a sec. If I'm looking at this data, I have no idea what I'm doing. I mean, well, let's see. I don't know where the center is. It appears that all the weights are somewhere between what, 114 and I don't know what, 172. That gives me some idea of variation. I don't really know where the center is. Technically, it's got to live somewhere between those two. I don't know if this 114 is an outlier because there's a 116. I don't know if the 172 is an outlier. I need a way to organize this data. And the way to do that is called a frequency distribution, okay? So what we're going to do, I'm going to show you how to build one of these guys. And then in class tomorrow, I'm going to show you how to use your calculator to make one too. After you can put you can input your data into your calculator and have it do the heavy lifting. But I really do want you guys to appreciate how things are done by hand, again, so that when you look at it, it's not garbage in, garbage out, because your calculator's an idiot box and it's only as smart as the idiot pushing the buttons. So the first thing that we're going to determine is something called class width. All right? So if I take the class width, the way that I take the class width is we're going to make classes, and the classes are just groups. And I want those groups to be even in width. Okay, so all that a group is going to be a set of numbers. Now, again, if we wanted to, we could order these numbers, but that's silly because by the time we're done with the frequency distribution, it'll be done for us. Now, classes are typically, the number of classes is the number of groups that the numbers end up in. And they're somewhere between, my general rule of thumb is between 5 and 15. The book says 5 and 20, but that to me is just a little bit silly. So in this case, I'm going to pick, I don't know, kind of randomly 6. I think there's somewhere around 28 data values. Again, we'll figure that out in a second, but 6 it feels good. Okay, so the way that you determine the class width is you simply take the max data value minus the min data value, whoops, and you divide it by, in this case, the number of classes, which is 6. Okay, so let's see, my max is 172, my min is 114, and I divide that guy by 6. Let's see, what is that? That's what, 58? Looks like 58. So 58 divided by 6. Now, something funky may happen here, and I'll show you what potentially could happen, but it'll be just a sec. All right, so 58 divided by 6 is what? 9 2/3, so 9.67 approximately. I'm going to round this up to 10. Now, in so doing, I may actually lose one of my classes. I may only end up with 5, which is okay. Okay? So here we go. Now it gets really simple. I know that the width, the size, think of it as the size of each one of my classes is going to be 10 wide. They're all going to be the same width. So I'm going to start at the lowest value, which is 114. And I'm simply going to add the width to it. Let's make sure, before I do that, when data like this sits in front of my head, my ADHD just starts to flicker. And let's see, I'm going to add 10, so I get 124. I think I'm good. And then I get 134, 144, 154, 164, and 174. Okay, so these are those classes. Now, remember, these classes are going to be, they're going to have a width to them. So what I'm going to do, now this may seem counterintuitive at first, I'm going to go right up to 124, but I can't go to 124. In other words, I can't write 124 here, and then I can't go from 124 to 134. And the reason is, if I have a data value that is exactly 124, it's going to end up in 2 classes. The classes need to be mutually exclusive as far as membership by the data. So the way that I ensure that is a little mathematical trick. It's not that big of a deal. It's not magic or anything. Is I just go to one number below. So this is 123. This is 133. This is 143. This is 153. And then I'm going to clean this up here in just a sec, and we'll put it over on this page to make it look prettier. 163, 173, and then 183. Okay? Now, this is where you may start crying out. You may say, Ripley, these are no longer, what we say, they had to be 10 wide. That's 9 wide. Well, what we do is we just take it, since the most precise value in these numbers is in the ones place, I'm going to go to tenths, and that I'll create classes. All right, so here we go again. These are classes, and sometimes you'll see this written as class boundaries. Okay, and watch what I do here. I'm going to go 113.5 to 123.5, and then 123.5 to, what do we need to be, 133.5? 133.5, and then 133.5 to 143.5. 143, guess I could have given myself more room, it is what it is, to 153.5. Now notice that my widths are all 10 now, which was promised when we did this problem. But now again, rightfully so, you might have just cause to say, wait a sec, but 133.5 and 133.5 are in 2 different classes. Yeah, but the data only goes to ones, so there's no way that the tenths we're not going to have a value measured in tenths. So I'm not going to have that overlap. They are guaranteed to be mutually exclusive because of the way that the data is. So 153.5 to 163.5, and then 163. How many do we have here? 1, 2, 3, 4, 5. Whoops. 163.5 to 173. How did I do over here? 1, 2, 3, 4, 5, 6. Look at that. I did 7. What a ding dong. Sorry. 163.5 to 173.5. We do all make errors. Okay? So, easy. Nothing to it. Now, what we're going to do is we're going to do a tally. Just a standard issue tally. And I do stuff like this just because, again, I will screw this stuff up left and right if I don't. All right? And I'm going to change pens, pen colors, just to be sure. Keep it nice and bright and obnoxious. Okay, so I'm just going to work my way through the data until I get all the way to the bottom, and I'm going to end up in each one of these. I hope you guys don't mind this, but I'm going to change the color over just to do this. And I'm going to go, sorry, I need a tool that draws perfectly straight lines, but the graph paper helps. Okay. Okay, and then, perfect. All right, come back over here. All right, so I'm on black, so I'm going to change that up. Pardon me, guys. Go over here and turn this thing blue. All right, so 155. Let's see, where's 155 going to end up? It's going to end up in there. 142, it's going to end up in there. 149 is going to end up in here. 130, if you catch me making an error, there's nothing you can do about it. 151, just kidding. Right here. 163, that goes right here. 151 goes right there. 142 goes right there. 156, speaking of garbage in, garbage out, right? 133, that's going to be right here. See how it's on the boundary line, but because it's intense, I don't have to worry about it. 138 goes right there. 161 goes right there. 128, where's 128? Right there. 144 goes right there. 172, it's way up here with this guy. Oops. 137, right there. 151, 166. 66 gets me there. 147. 147 is here. 163. I got to be careful. It's starting to get a little punchy. 145. 116. 136. 158. 114. Whoops. 114. 165. If you're bored as heck, you can always fast forward through this. 169 right here as well. And then 145, which is right here. Okay? Now, let's see what we got. What I'm going to do, and the reason that this is called a frequency distribution is because we then write down the frequencies, which is typically written as f. So for this guy it's 2, for this guy it's 3, for this guy it's 5, this appears to be 8, this is 6, and this is 4. Let's see what I got here. I got 10, I got 28. Hey, look at that. N equals 28. That's kind of cool, huh? All right, now, sometimes the way that you'll see this written is, excuse me, the way that you'll see this written as it's written with midpoints. So you'll sometimes see this written as x sub n, or you'll see it this m implies midpoints, or you'll see it written as midpoints. So we can simplify this whole thing that I have here into just this easy peasy little deal. All right, so to find the midpoint of that, I simply have to add 5 to this, and that gets me to the midpoint, right? You agree? So this would be 118.5. Let's see, 128. It's easy to figure these out because once I have the first one, I can just add the class width to get to the next one. Does that make sense? You can't respond. 148.5, 158.5, and then 168.5. And then you'll see it written with 2, 3, 5, 8, 6, whoops, 6, and 4. That's supposed to be a 6, and with n equals 28. Now, the rationale behind writing these with midpoints is that in theory, statistically speaking, all of the data values in each one of these classes are going to cluster around the middle of the class. Now, whether that happens or not, it doesn't really matter. But I do want to show you the power of a frequency distribution. Check this out. If I think about this, if you take your head and you twist it to the right, look at what I have. I have this very cool distribution now. This thing looks like, it kind of looks in a very rudimentary form. It looks like one of these guys, doesn't it? So I can start thinking to myself, if I could turn this thing horizontally, if only there were a graph that I could use in statistics. Well, I'll teach you one of those here in just a sec. If I look at this thing, it's like, oh, graphically speaking, I can already see that this thing's going to have a shape. Whoops, I did a little writing there, didn't I? When I graph this thing, its distribution is going to look like that. Doesn't appear to be any outliers. My center is going to be somewhere in here, which is exactly where you would expect. Let's see, our variation is really easy to figure out. I go from about 113.5 to about 173.5, and we're all good. I'm going to try and erase my strange move over here, which you guys all wanted to tell me I screwed up on, and you couldn't. So that is a frequency distribution in a nutshell. We will get into some more tricky ways to deal with these frequency distributions down the road. I'm going to give you guys a little break and let you walk away from this for a little while, and then when I see you, we'll come back and we'll get a little more information from our frequency distribution. It's a really super powerful little chart that we can use to really organize our data, and then we get to start presenting our data and start making decisions based on what we see. All right, thanks for your attention, and have a really good day. Welcome back, everybody. I hope you all had a nice break. Hopefully you didn't get too many wet willies this thing happens. So we're going to do a little more work with our frequency distribution here really quickly, and then we'll be done for this little lesson. We'll get into some more graphs in the next lesson. Okay, so remember, this was our data. We took our data, we went through, found the class width, we built our classes, and we just used our tallies by crossing out the data as we went. We created class boundaries or class widths. It can be written either way. And then with our frequencies, we can clean it up with our midpoint right here. Remember, this guy right here is our midpoint of each one of these classes. So there's lots of ways to do that. Now we're gonna have a little bit more fun with this because we can get a lot more information out of a really simple little distribution here. But I need a little more room. So over here on this page, I did a little erasing. I'm going to do something called relative frequency and cumulative frequency. So I might also do a cumulative relative frequency, but that just seems silly. All the cumulative frequency is I'm going to write it as a new column, so I'm going to have CF, and I'm going to write a 2 here because the first class has 2, and then all I do to fill out the chart is I write out for each one of the widths how many of the total. Remember down here n equals 28, that's how big our sample was. I'm going to write these out as they accumulate. So when I go to my second width, I pick up the 2 from the first, the 3 from the second, so this guy's a 5. All I'm doing basically is adding this to get this. All right? Now, for this guy, I have 2 plus 3 plus 5, and I get 10. Really, think about it this way. I add this guy to get 5. I add 5 to 5 to get 10. I'm going to add 10 to 8 to get 18. So this class right here picks up 18 plus 6, which is 24, and then 24 plus 24 is 28. It's nice because this number should always equal the total in n. Okay? So basically what that tells us is how much of the classes, for any given class, how many data values are at that class or behind. And we'll use that a lot more down the road with something called percentiles, but we'll get to that when we get to it. The other thing is we're going to talk about relative frequency. So we're going to do RFs. I should probably write that down. CF equals cumulative frequency, and RF equals relative frequency. All right, and all the relative frequency is it's the frequency of that specific class relative to the others, to the total. Excuse me. So what we end up with is a percentage. So the relative frequency for the first class is 2/28, which is 1/14. Let's see. I'm cheating, you guys. I hope you don't disrespect me. So about this is about 7%, so 0.07. All right, this guy's going to be 5/28. 5/28 is about 18%, so 0.18. And I can write this as a percent if I wanted to. This is going to be 10/28, which is 36%. You got to be a little bit careful here because you're going to have to give up a percent somewhere, because remember they all got to add up to 100% when everything's said and done. Wait a sec, I screwed that up, didn't I? I don't want 5 and 18. Excuse me. Try that again. That would be the cumulative relative frequency. Let's try that again. This one's going to be 3/28. It's good to see your instructor make mistakes. Let's see, 3/28. So that's going to give me about 11%. So 0.11. 5/28 is about 18%. So I guess I wrote that earlier, didn't I? 8/28 is about 29%. Again, I'm going to have to give up a point here at some point, but I'm not afraid. 6/28 is 21%. And then if I needed to, let's see, that's going to be 18, 36, 65, 86. So this guy should be about 0.14. Let me check it for, yeah, 1/7, right? 0.14. And I know that this sums to 100% or 1. If I wanted to do the cumulative relative frequency, that'd be the CRF. This is kind of useful for percentiles. I just add them up. So same way as we did before. This would be 0.07. I go from here to here. I get 0.18. Go from here to here. Excuse me. I get 0.65 and then 0.86. And then hush my mouth, I get 1.0, which is the same thing as 100%. Okay, so that's about as much as you can do with the frequency distribution as far as being useful and giving us some data that we can play with down the road. In the next lesson, what we're going to do is we're going to take these frequency distributions and we're going to put them on graphs. Some graphs lend themselves really nicely to frequency distributions, others not so much, but I'm just going to give you some examples of some graphs, and then we'll be done. All right? Hope you enjoyed the presentation. Have a great day.